Hello, I am Erdem from Vision. In this video we will see how we can analyze circuits by node analysis and by constructing a supernode. Remember the first step of the node analysis. It was to choose a ground node, and I am choosing this node to be the ground. And second step is to assign unknown node voltages, and I'm labeling this node as the node A, and I'm assigning EA node voltage, and this is the node B. Let's say this has node voltage of EB. Okay, remember the discussion of the supernode. We are constructing a supernode if two nodes other than the ground node is connected with a voltage source to avoid unnecessary current labeling. Right? So let's construct a supernode like this, and left terminal of this supernode has a node voltage of EA, and the right terminal of this node voltage this node has a node voltage of EB. Okay, now we should write KCL equation as the third step, and since we have one single supernode, we must have one KCL equation. So let's write KCL at supernode. There are three currents related to supernode, and the first one is this independent current source. It's entering to the supernode, which means you should write minus I1. We don't know current through R1, and that's assumed to be away from supernode. And notice that R1 is connected to the left terminal, so voltage across R1 is simply EA minus 0, and if we divide this by R1, we can find the current value. Again, we don't know current through R2, and that's connected to the right terminal of the supernode, which means it has a voltage across it with value EB, and we divide this by R2 to get current value. We have included all three terms in KCL, so we can write 0 is equal to 0 by KCL. As we see, we have two unknowns in this one equation. We must have one more equation to solve this system actually, and we will write that equation at the construction of the supernode. Notice that we have labeled this as the EB, right? As the node voltage EB. And while going from node B to node A, we have increase in voltage by the value of V1. So we will write, or we can write, EB plus V1 is equal to EA. And this equation is called constraint equation. I want to tell you one thing. Let's send this out of the screen, and I will redraw whole circuit. This is R1. This is the current source. Okay, and polarities are like this. Let me label the components also, R1, R2, and V1 here. Assume that we have labeled this as node B and it has a node voltage EB. Alright? Instead of labeling this instead of saying that this node has a node voltage of EA, we can actually directly write this node A has a node voltage of EB plus V1. Actually, I have directly written EB plus V1 for EA. So if you directly label the node voltage of node A as EB plus V1, you don't need to write a constraint equation in the equation system. So let's apply KCL for this KCL at Supernode again, Supernode, and we have a supernode like this, and one terminal has a node voltage of EB plus V1, and one terminal has a node voltage of EB. Okay, I1 is entering to the supernode. So that's minus I1. We don't know current through R1. Voltage difference across it is EB plus V1. And we divide this by R1 to find current value. And we don't know current through R2, and it has a voltage difference across it EB. We divide this by R2 to get current value, and this whole equal to 0 by KCL. And notice that we have only one unknown here. And this equation could be solved actually. That's all for this video. Thanks for watching.